Hi, and welcome again to my Physics Online video lecture series. Today's lecture, we're going to be talking a bit about AC signals as applied to inductors. So we've already talked, if you've been watching these in order, about AC signals through resistors and AC signals through capacitors. Today we look at AC signals through inductors, and then in a future video maybe we will put everything together and look at circuits that contain all three elements with AC signals. So at this point the basic plot should be kind of familiar as to what we're going to be doing. In the previous videos we discussed a few things like what does voltage look like given a current? Or what does voltage drop look like given a current, e.g. Something like I is equal to I naught cosine omega t. And for the resistor, what we ended up getting was that V sub r, or if you prefer delta V sub r, was equal to I naught times r times cosine omega t. For the capacitor, what we ended up getting was that the voltage drop, we could call this delta Vc, looked like essentially I naught times some reactance, we could call that X or chi sub C, and then we ended up with a cosine term but with some phase difference. So the cosine ended up being cosine omega t minus pi over 2. So we might say in these cases that current and voltage are in phase. For the resistor, so that means peaks and troughs line up, or peaks line up with peaks, troughs line up with troughs, etc. This one we would say current leads voltage, and then for the inductor we'll see what it looks like, but we need to remind ourselves what chi c represented was what's called inductive reactance. And so it was given by 1 over omega times c, where omega is the frequency of the applied current. So this was capacitive reactance. Okay, so what about for the inductor? So if you have a loop that includes an AC signal, so there's my signal, and then it also includes an inductor somewhere in the loop, and that's basically it, then we expect to have something where the induced EMF, and ergo the voltage drop across this, matches the rate change of the applied current. So we have I naught cosine omega t once again, and so loop rule basically, or put differently, the delta V for the inductor should be equal to the induced EMF. We know that the induced EMF for an inductor is negative L times rate change of current. That is, in fact, the whole point of an inductance. And so if you were to follow a sort of loop rule for this system, the sort of like loop rule for the system would end up basically saying something like delta VL minus L delta I over delta T equals 0. And essentially the way that this ends up working is like looking at this, and looking at the equation up here. This rate change of the current turns out to be given by essentially I naught omega times sine omega t. It's negative, but it's basically like that. And so if you were to solve, what you'd get is basically delta VL, basically like adding this to both sides and all that. Delta VL would basically look like I naught omega L sine omega t. And it's worth noting that sine omega t is the same thing as cosine omega t plus pi over 2. So what we expect here is to have basically the voltage leading the current. So voltage leads current for an inductor. So let's see what that would look like. Essentially, we would expect, if we were plotting these two things, you'd get a graph like this. So this dashed blue line would be basically your voltage. The solid black line would basically be your current for the inductor. So this is inductor. Oops. And the way that the inductor works, therefore, is that you have voltage leading current. So like the peak for the voltage occurs before the peak for the current. So blue dashed line is the voltage. That would be this guy. Black solid line would be this guy. And notice that the features on the blue line are to the left of the features of the solid black line. Basically means that they're occurring earlier in time. This is a time axis. Okay, the other thing to note is that we could look at the peak values. So this right here, this peak value would give me I naught if I were to come across like here. This peak value right here gives me delta VL max or delta VL naught. And just as we did with the capacitor, we can write that there exists some reactance value which is defined as this ratio. And so it'd be basically like the peak of my voltage curve divided by the peak of my current curve. And so if you do all that, if you come back to the equation that we found, we can say that I is given by I naught cosine omega t. We can say that delta VL is given by I naught omega L cosine omega t with that phase factor added. And so we look at basically the amplitude terms of these two. And so what this gives us, stay on this page, what this gives us is that XL or chi L is I naught omega L over I naught, but that's just omega L. So if we go back to our original summary slide, so we can add to that slide this new thing for the inductor. We get delta VL is equal to I naught chi L cosine omega t plus pi over 2. And where chi L is equal to omega L. And so this one right here, we could say voltage leads the current. So and up here it says leads as well. So voltage leads current for an inductor. And this right here would be the inductive reactance. So now we've got all three sort of resistive terms or reactance terms. And recall that up here, R was essentially our equivalent to a reactance term. So in a future video, like I said, I will put all three together. But for right here, these are basically sort of your three major terms for this Physics 2 course. So let's do maybe a couple quick examples. So our first example is to determine the reactance for an inductor when a given current is applied to it given the inductance. So straightforward example, chi L would be equal to, essentially we expect omega L. This right here actually is L, and this term right here that multiplies the time in the cosine, this is your omega term. So I have 2,000 radians per second times 0.50 millihenry, which needs to be converted to henries. So 10 to the minus 3 henries per millihenry. And what that gives us is essentially a reactance of 1 ohm. So very straightforward there. Let's do another example. All right, for our second example, you have a set of curves. It's the same set that I showed before, but maybe let's go ahead and get the reactance and the inductance. So to get the reactance, we basically need to know what the peak value is for the current and what the peak value is for the voltage. So this right here corresponds to 1.0 volts. This right here looks like maybe 1.25 amps. So if I'm trying to find the reactance chi L, that should be delta VL max divided by I naught. And so that is 1.0 volts divided by 1.25 amps. Okay, so that gives us a reactance of basically 0.8. 0.8, maybe 2 sig fig, 0.80 ohms. Now for the other part, we're trying to figure out what the inductance is. So this answers part A, determine the reactance. For part B, get the inductance. We'll say starting down here, we know chi L is omega L. We know that omega, so L would be chi L over omega. We know that omega is given by 2 pi divided by the period. So coming over here to this graph, we want to figure out the period. I have 1, 2 oscillations in 4 seconds. So like 1t, 2t. So 2t is 4 seconds, therefore t is about 2 seconds. So that means that chi L is equal to, that L is equal to about 0.8 ohms divided by omega, which is itself 2 pi over 2.0 seconds. So this gives me 0.8 divided by pi. Yeah, that's a bit more than I can calculate in my head, but looking at my calculator, that comes to about 0.254. So we'll call it 0.25 henries. And that's how much inductance this system has. All right, so that's 2 examples for this short video. And I think I've covered all that I was going to in today's video. So thanks for watching, and hopefully you learned something from it. See you in the next one.